So someone wrote and asked me to do some of these review problems, so I'm going to go through and just give, the hard parts of several of them. So for this one, you can use sine 2x equals 2 sine x cosine x. We've used that identity a couple times, mostly in the triangle part of trig sub to go back to the original variable. So if you do it here, then the integral that you get is 2 sine squared x cosine x dx, and then this becomes an easy u equals sine x. Let's go to the next one. Cosine squared 79x is just equal to 1/2 plus 1/2 times cosine. What's 2 times this? 158x. And then this is easy. Here, what do? You convert to secants. Stupid thing. Why is this not grabbing that? So tan squared x is equal to secant squared x minus 1, and then that's an easy integral because the antiderivative of secant squared is just tan, and everybody knows the antiderivative of minus 1. For this one, I would write it all out in terms of sines and cosines, so tan cubed x is sine cubed x over cosine cubed x. So when you do this, what you get is these cosines cancel, and you get cosine squared x and sine cubed x dx. And then what you can do is feed out a sine and then convert everything to cosine. So you get cosine squared x 1 minus, mistake, 1 minus cosine squared x times sine x dx. And then you can just do u equals cosine x. And then it becomes easy. For this one, let's see if you can just feed one out here. What if you put out a secant x tan x? Yeah, that's what you should do. So this is the same thing as tan squared x secant to the 6th x times secant x tan x dx. So the thing to observe here is that if you substitute with u equals secant x, then that's du. So you'll just convert these tangents to secants. So you get secant squared x minus 1 times secant to the 6th times secant x tan x dx. And then you just do u equals secant x. Okay. So next problem. Oops. So you can just do, just feed out a sine. Oh, my daughter's coming. Hi, how are you? Sine squared 15x. You haven't gone to the farm yet, huh? You're going to the farm?
Daddy's working.
Yeah, Dada's working. His students never leave him alone. They hate him, and yet he works his fingers to the bone for them. So now convert these to...
He's making a baby parrot toy.
Yeah, I'm making a baby parrot toy for my students. Do you think they'll appreciate it? Oh, you're going to take my pen.
Dada put you in his eye.
Okay.
Let's
All
have
right.
the grits before we leave.
Oh, you're about to eat some grits. That's going to be great.
What did you convince your dad to do?
We're going to look at baby parrots.
Doesn't she look adorable? She's taking the worm with her.
Oh, you've got your apple costume on.
She's
That's
going to
perfect
show
for
the
the
worm
farm.
to goat Jack, although I don't know if the other goats came, and they were supposed to have 2 donkeys join them and some sheep. They have baby sheep, but I don't know if the goats have arrived.
Oh, the goat Jack, that'll be so wonderful, honey.
Mm-hmm. We'll show him.
You'll come back.
Be sure to take
We
some
will.
quarters for the corn.
You'll come back.
Actually, we cut up an apple, and Jack was so happy with an apple last week because he's tired of the corn, Dada. Everybody gives him corn. So he was Marin's best friend with that apple. Marin would take a bite, give him the other half. Take another bite, give him the other half. And Jack and her were in goat land. Are you ready? Want to cut an apple?
Yeah.
Come on, let's go cut an apple for Jack. And I think you should have a little bit of your grits.
He's coming back.
Yeah.
Oops. Secant squared x tan x minus tan x dx. And this one is, I think it's minus natural log of cosine x, something like that. You can figure it out on your own. I'm not swearing that that's the answer. And for this one, you just do u equals tan x. And then it's easy. So for this one, by the way, if you're just watching me do these, this is like entirely the wrong thing to do. If you don't try to do it yourself, you're not going to get any benefit. Secant to the fourth. I'm going to punt on this one because I don't know for sure what to do. What do you do? Integration by parts. I think maybe you try integration by parts. Let's try it. Oh, okay, yeah, so let's try integration by parts. We've got secant squared x over 2, secant squared x over 2 dx. And now if you do integration by parts, you can do dv equals secant squared x over 2 dx. And so you integrate that, and v is equal to tangent x over 2. Now you've got to consider the chain rule, so multiplying by 2 will solve the chain rule issue there. And this is going to be u. Okay, so you take the derivative of this, and you get 2 times, I'm going to go one line down, it's kind of long, du equals 2 times 2 times secant x over 2 times secant x over 2 tan x over 2 times 1/2. And can you clean that up a little bit? That turns into 2 times secant squared x over 2 tan x over 2. And now you do integration by parts and you get u times v. I'm just going to skip that because it doesn't have anything to do with, I mean, it's just part of the answer. It has nothing to do with this approach being feasible. So let's see what happens here when you get v du. You get, there's an extra tangent here, so you get 4 times secant squared x over 2, and then this tangent combines with that tangent and gives you tan squared x over 2 dx. Alright, so now what can we do? So now just do u equals tangent and you're done. Because du is then secant squared. That one's kind of tough. start trig sub, and the substitution for this one is x equals 3 sine theta dx equals 3 cosine theta d theta. And when you go inside the radical here, the radical 9 minus x squared becomes 3 times cosine theta, and then the integral that we get is 9 sine squared theta for that x squared on top, and the thing in the under the radical turns into 3 cosine theta, and dx turns into 3 cosine theta d theta. Alright, and you get some cancellation here. Zoop! Zoop! And you just have to integrate sine squared, which is very easy. This is 9 times 1/2 minus 1/2 cosine 2 theta d theta, which is equal to 9 times 1/2 theta minus 1/2 sine 2 theta times 1/2. And now we have to play the triangle game. So for the purposes of playing the triangle game, you want to further write this as 9 times 1/2 theta. I'm just going to combine these two to make a fourth, and this becomes 2 sine theta cosine theta. And now you're ready to do the triangle. You know, and what's the original substitution? The original substitution is x over 3 equals sine theta. So you set up your triangle to make that true. X over 3. You ask yourself, what's cosine? Cosine theta is going to be equal to, oh, we have to do this part. This is the square root of 9 minus x squared, the original radical. And so this is adjacent over hypotenuse, which is 3 over the square root of 9 minus x squared. And what about this theta? You just apply inverse sine. So theta is equal to sine inverse of x over 3. You just combine all that stuff and write it in for the thetas, and you're done. So these take quite a while. And I want to try to go through all the problems, so you can just see here the substitution that you should use is x equals 5 tan theta, and then you do the rest. Alright, next. This is x equals 2 tan theta, and you do the rest. This one is a little tricky. Let's erase this stuff. So how do you know what to do here? You have the square root of 25 minus 81 x squared. So the substitution here is going to be something like a times sine theta. And what kind of properties do we want a to have? We want a times 81, or sorry, we want a squared times 81 to be equal to 25, so that you can factor out the 25s and also cancel the 81. So a is going to be equal to 5 over 9, and then you can do the rest. This one is just x equals sine theta. This one is just tangent. Alright, so this one is something new. So this is partial fractions. You have x plus 9 equals a over x plus 8 plus b over x plus 9. And 1 is equal to a times x plus 9 plus b times x plus 8. And now you make the strategic substitutions. X equals negative 8, in which case 1 is equal to a. And if x is equal to negative 9, well then 1 is equal to negative b. So a is equal to 1, negative 1 is equal to b. And so the answer to this problem is, if you go back up here, integrating the left-hand side is just the same as integrating these two. So you're going to get natural log of x plus 8 minus natural log of x plus 9 plus c. Next. Yeah, so this one is also partial fraction, so this is the same thing as 8 minus x times 8 plus x by difference of squares. So you have to find some way to write this as a over 8 minus x plus b over 8 plus x. And so what do you get? 80 is equal to a times 8 plus x plus b times 8 minus x. And now you do strategic substitution. X is equal to 8, and then 80 is equal to 16 times a. And so 8 goes into both sides. You get 10 equals 2a. So a is equal to 5. And over here you can do x is equal to minus 8. And then 80 is equal to 16b. And so b is also equal to 5. And you can do the rest. Oh my god, do you have to complete the square? So this is either an irreducible quadratic or it factors somehow. So let's see if we can factor it. Let's just look at the discriminant from the quadratic formula. That's b squared minus 4ac. So what is that in this case? This is 121 minus 98, is that right? 4 times, no, 96. I think it's 96. Which is a positive number. Okay, so that means that this polynomial factors. So the question is, what does it factor into? And can we think of two numbers that multiply to be 24 that add to be positive 11? 8 and 3. Alright, so x squared plus 11x plus 24 is equal to x plus 8 times x plus 3. And so what you get is 1 is equal to a times x plus 3 plus b times x plus 8. And you do the strategic substitution. X equals negative 8. So 1 is equal to minus 5a, and minus 1/5 is equal to a. And x is equal to negative 3. So 1 is equal to 5b. So b is equal to positive 1/5. And you can do the rest. So, oh my gosh. Now we need to check if this is an irreducible quadratic or not. So let's check the discriminant. Square root of b squared minus 4ac from the quadratic formula. If this is negative, then there are no roots. If it's positive, then there are roots and it's reducible. So which one is it? We get the square root of 81 minus 32. Okay, which is positive, therefore there are real numbers that are the roots of this quadratic, so it is reducible, not irreducible. Alright, so what are those roots then? We need numbers that multiply to 8 that add to 9. Oh, so those are clearly 8 and 1. So we get s times s plus 1, s plus 8. And on top here, now you have 8 times s plus 1. Oh, interesting, there's a cancellation. Zip. And so you get 8 over s times s plus 8. And you just do this, you know, the way that we've been doing it, etc. Okay, so you need to actually do it because you haven't been doing it for 20 years. Okay, this one is a little bit tricky because notice that it's an improper fraction. The degree of the top is bigger than the degree of the bottom. So you have to do some long division. So let's multiply out the bottom. The bottom becomes x squared plus 3x plus 4x plus 12. So we want to send x squared plus 7x plus 12 into the numerator. There's a terrible line. I need a straighter line. The numerator is x cubed plus 0 times x squared plus 0 times x plus, minus 3. Right. So how many times does this go in? X. And you get x cubed plus 7x squared plus 12x. And now you subtract and you get minus 7x squared minus 12x minus 3. And then you can do minus 7 and you get minus 7x squared minus 14x, and this becomes minus, 70 plus 14 is 84. And so you get the difference here is 2x, and this becomes 81. So 2x plus 81. Alright, so what we've just shown is that x cubed minus 3 over x plus 4 times x plus 3 is equal to x squared plus 7x plus 12 times x minus 7 plus 1 over 2x plus 81. And so by the time you get done, there's no partial fractions necessary. So this is just, this one is a u substitution, and this one you just multiply it out and use the power rule. Next. Okay, so that's definitely an irreducible quadratic there on the bottom, but again, this is not in least terms, so you have to do some polynomial division here. X squared plus 81 goes into x squared plus 0x plus 0, and just go in one time. You get x squared plus 0x plus 81, and the difference is minus 81. So x squared over x squared plus 81 is equal to x squared plus 81 minus minus 81. Oh, that's not right. Hold on, let me pause the video. Okay, sorry. So the mistake that I was making here is that this denominator should not be there. So this is correct. And so this means that we can divide through by x squared plus 81 to get the quotient. X squared plus 81 is equal to 1 minus 81 over x squared plus 81. And now to do this integral, the hard thing is doing this integral. So the integral of, first you have to do partial fractions on that part. So 81 over x squared plus 81 is just one irreducible quadratic factor, and you get ax plus b over x squared plus, oh, what am I saying? I'm sorry that my ability to do calculus has totally declined in the last 5 minutes. Also, I need to go back and do the previous one because I realize I messed that one up too. This one is just trig sub. So if you want to do the integral of 81 over x squared plus 81, just do x equals 9 times tan theta. And there should be a dx there. Okay, so that will solve this. In fact, this one is just really close to arctangent. It's going to be some constant times arctangent. So let's go back and try to fix the mess that I made of the previous one. Is my work still there? Yeah, so I made a similar mistake with this one. So what did I do here? The thing is, this denominator should not be there for this equality to be true. So what's true is that x cubed minus 3 is equal to not this, but just that. I apologize. Okay. And so now what do you do to fix it? You divide both sides by the denominator. And then when you do that, let's see what happens. I can't seem to scroll down anymore, so I'm just going to do it right here. So now add the denominator to both sides, 7x plus 12, and you do the same thing here. X squared plus 7x plus 12, and so you get cancellation of this in this case, so you get x minus 7, and over here you have to add in the denominator. So this goes over, and let's just go ahead and use it in factored form. So this is still x squared plus 7x plus 12. I'm just writing it in factored form. X plus 3. And so now you have to use partial fractions decomposition on that. So let me copy this. Oh, I didn't copy all of it. Sorry, I'm going to try to get a better copy. Whoops. Control C. Are you listening to me, computer? Control C, and now clear all this stuff. And paste. Alright, so this is equal to a over x plus 4 plus b over x plus 3. And you get 2x plus 81 is equal to a times x plus 3 plus b times x plus 4. Alright, and now you start doing your strategic substitution. So x equals minus 4, and then you get negative 8 here. So is that going to be 73? I believe so. So this is 81 minus 8 is 73, is equal to minus a. So a is equal to negative 73. And for this one, you do x is equal to negative 3, and you get b is equal to, this is 6, so what happens when you take 6 away? You get 75. So b is equal to 75, and a is equal to negative 73. All right, and then you just complete the integral normally. So, all right, for this one, we need to do, so it's definitely not improper. The question is, does the bottom factor? So what are two numbers that multiply to 15 that add to 8? They have to be 3 and 5. Yeah, it's 3 and 5. So you've got 10x plus 36 over x plus 3 and x plus 5 is equal to a over x plus 3 plus b over x plus 5. And so I just kind of want to say etc., but let's go through it. So you've got a times x plus 5 plus b times x plus 3. Now if you go ahead and fail the exam on Thursday and you watch the video, you can say, well, I watched the video, so I'm making this video, but it doesn't let you get around the problem of, like, you know, looking at a math problem and wondering what to do, and your stomach burns and your head aches and you get an earache and your hand trembles. You need to do that. Watching this video is not going to solve any problems for you, unless you've tried to do these problems on your own and gotten stuck. So if you're just sitting there slack-jawed, drooling on your lap in the subway, watching me do these problems, it's not benefiting you at all. You have to do these problems on your own and then use the video to resolve any confusion or to help you get through a tough place. Like, that's the point of something like this. You go to say, I failed the exam, professor, but I went to the tutor. It just makes me want to, vomit right in a student's face. You sit there, you talk to a tutor, you might notice that your brain doesn't hurt while you're doing that. You have to do something that makes your brain hurt to get ready for the exam. There's just no way around that. So now what do? Strategic substitution. X equals minus 3. You get negative 30 here. This becomes 6. And so you get a times 2 is equal to 6, so 3 is equal to a. Here you do x is equal to negative 5. This gives you negative 50. So on the left you get negative 14. And on the right you get negative 2. So b is equal to 7. And then etc., etc., etc. Have we already done this one? So this is an irreducible quadratic factor. This one is an interesting mix. So let's do it. So you have to write this. This would, skipping writing the left-hand side, this is equal to some a over x plus 5 plus bx plus c over x squared plus 16. And now if you clear all the fractions, what you get is 1 is equal to a times x squared plus 16 plus bx plus c times x minus 5, x plus 5, sorry. Okay, so this gives me a times x squared plus a times 16 is equal to b, sorry, not equal to, plus bx squared plus 5bx plus cx plus 5c. Alright, so now we have to collect like terms. 1 is equal to x squared times a plus b. And what about the linear term is going to be x times 5b plus c plus the constant term, which is 16a plus 5c. Alright, and from this you get several equations. I wish you could push up instead of pushing down. But with my little thing I can't. So I will copy this, push everything down. Let's work on this some more. So this gives rise to 3 equations. So there is no quadratic term on the left, so you know a plus b must be equal to 0. And there is no linear term on the left, so you know 5b plus c is equal to 0. There is a constant term which is 1, so you get another equation which is 1 is equal to 16a plus 5c. Alright, so now you have to, let me write this over here. This is equal to 1. So you know that a is equal to minus b. Alright, so I'm going to multiply this one times negative 16 and add it to that one. And then what's the result? You get 0 a's, which is the point, minus 16 b's, plus 5 c's is equal to 1. And now with these two equations, you have 5b plus c is equal to 0, and also this. So this one tells you that c is equal to 5b. So what if you use that down here? Then you get minus 16b plus 5c is the same thing as 25b is equal to 1. So this means that 9b is equal to 1, so 1/9 is equal to b. Alright, so if 1/9 is equal to b, then a is equal to minus 1/9. And then what does c have to be? C is equal to 5 over 9 because it's 5 times b. Okay, so now you know all of them, and you can just do the integral. And how many problems are there? Like 40? I'm getting tired. So let f be a quadratic function so that f of 0 is equal to 4. Yeah. Determine the value of f prime of 0. Never thought about how to do this problem before. I think I better pause the video and think for a second. Okay, I think I see a strategy for solving this problem, but I'm not going to do it. So first of all, do this integral using integration by parts, and then you will get some kind of solution. And then take the integral twice of both sides. Sorry, take the derivative twice of both sides, and then that will give you an expression involving f prime on the left and some mess on the right, and then you can just solve for f prime. Not gonna do it. This one is easy. They tell you the answer. Yeah, this one is pretty easy too. Two numbers that multiply to 7, that add to 7 and multiply to 12, those are 5 and 2. This one is improper, so you have to do long division first. Be careful. This one is just you could do it as trig sub, or you can use partial no, you can't do, yeah, you could try trig sub, but you could do partial fractions too. We'll just look at the solution. There you go. And this one is trig sub, and there's no partial fractions, so they get around to doing any kind of substitution here. What are they doing? Oh, sorry, the category has changed, so now we're doing improper integrals, and this integral is improper because at one of these limits, namely either one, either positive 3 or negative 3, you get 0 in the denominator. So if you were to look at a graph of this, you would see like two asymptotes, and so you have to carefully do it using limits. And this one has a solution, so I don't see why I should do it. This one has a solution too. I assume that you guys can see the solutions, but just in case you can't, there it is. This one also has a solution. Okay, for each of the following improper integrals, carefully use the comparison test to decide if the integral converges or diverges. Give a reasonable best comparison function that you use in the comparison. So carefully use the comparison test, huh? So I'm going to pause the video and think. Okay, I see that there's a solution here. I didn't notice that. So I was confused because I didn't think you were allowed to do this. Like often these comparison things, they amount to just doing the p-test. So we talked about this in class, and you know, as I remember, there's just no way I don't know how to teach the p-test without just making people's brains ooze with boredom. But you know what? I think this might actually be incorrect. Huh. Sorry. Need to pause the video and think about this. So this problem is using a version of the p-test that I actually did not know. So if you look at in class, we talked about the integral from 1 to infinity of 1 over x to the p dx. And so what we said is that this diverges if and only if p is less than or equal to 1. So what they're doing in these problems is a little bit different. Instead of looking at the long brontosaurus tail, they're looking at something more like the integral from 0 to 1, some finite number, it doesn't matter, 1 over x to the p dx, and terrible picture. So the kind of thing that we're examining now is what happens like to this dinosaur tail. So this is sort of like the dinosaur tail that goes the other way. And it turns out that the rules here are a little bit different. So should we go through and prove it really fast? Let me just skip some of the steps. I just did it out here on paper. So if you do this integral carefully, then first consider what happens if p is equal to 1, then this diverges. You can work that out for yourself. Okay, so in the other cases, then you integrate this using a power rule, and what you get, you end up with the limit as t goes to 0 from the positive side of 1 over 1 minus p times 1 minus 1 over tp times t. Okay, and now, so this is the thing that you should focus your mind on here. So if p is greater than 1, then this is going to be sort of like 1 over t to some little positive amount. And then as t goes to 0, this is going to go to infinity, which means diverges. Okay, so if p is greater than 1, then this diverges. So notice that that's the opposite to the infinity rule. So something slightly different happens here. Now if p is less than 1, then what we have is like more like t to some epsilon, which is some little positive part here. And now as this t goes to 0, it just goes to 0. And so this whole expression converges. And so for this sort of vertical brontosaurus tail, the rules are reversed compared to what they are for the infinite integral. And these are all using, so these two are using the vertical brontosaurus tail rule that we just talked about, and this last one is using the infinite brontosaurus rule, where it converges if and only if p is greater than 1. And I have no idea what's going on with that last one. But those are good rules to know. So you only really need to know the horizontal brontosaurus tail, because that's the only one that's in our book, and that's the only one we talked about in class. Next. Oh my god. Alright, I guess we'll just have to suffer through it. To be honest with you, I'm getting tired of doing these. I think I might just stop soon. So it says, suppose that g of x is equal to x to the minus 2.5 and j of x is equal to the hyperbola. So here's j of x, that's the hyperbola, and g of x is 1 over x to the 2.5. So it says the area between g of x and j of x from 1 to infinity is, and the answer is infinite. So the area under j is going to be infinite because of the p-test, right? It's this is a j is p equals 1, which diverges. Meanwhile, this is p equals 2.5, it converges. And if you set up this integral, it's the integral of j minus the integral of g, and so this is going to be an infinite amount minus a finite amount is going to be infinite. And what about f? F is even smaller than g, and we know that g converges, so f converges. The integral from h from 1 to infinity, so here's h. H is above g but below j. Okay, so this one is a little strange, all right? So we know that you can't use the comparison test, but you can sort of use the p-test. I can see this one. So if we know that h is a p expression, so suppose we know that h is equal to 1 over x to the p for some p, then that p must be less than 1 because it's below j, which means that by the the p must be greater than 1. So by the p-test, h would converge, okay? But there's no way to be certain that h actually is a function of that form. And the comparison test doesn't help. You know that h contains a finite region and is contained in an infinite region, and for that reason I would say impossible to tell. So let's just check the answer here. Oh, it only does 1 and 2. So in that case I'm going to check my answer and see what it thinks about what I put for number 3. Okay, yeah, so it turns out to be can't tell. All right, and for k equals 1 to infinity, where is k? So k diverges because it contains the infinite region, which is the region under the j. And for p here, which I guess is this bouncy red one, it's contained in a finite region, which is, it seems to be eventually contained under g, which we know is finite, so we'll say that it converges. And q, where is q? Oh, q is up here, definitely diverges because it's containing infinitely much area. So let's do a quick check, since the solution doesn't cover all of those, and we are right. This one is, it diverges, so that's because it's a line going straight up. I mean, it's going up at 45 degrees, so of course it's going to be like an infinitely big triangle. It's going to have infinite area. So the answer is F. Oh, sorry, but this is in the denominator. God, please just erase the last 5 seconds of things that came out of my mouth from your brain. I'm getting really tired. This is a hyperbola, so it's comparison test with 1 over x. So you have 1 over 2 plus x is really similar to 1 over x. It's smaller than 1 over x. So it seems like it might have some prayer of converging because this one, diverges, but this one is smaller, so maybe it converges, but something like an additive constant like that is not going to make a difference. And I know what I'm saying is kind of loosey-goosey, and we haven't been over the theory that would really justify that. I guess you can just not use the comparison test. It looks like the solution here actually just does the integral hardcore, so then you can see the hard way that it diverges. So this would be, you're probably going to want to use the comparison test. Let's see if we can use the comparison test on this one. So the natural thing to compare it to is 1 over the square root of x. So x minus 3. So this one is a little bit bigger downstairs, so the whole thing is smaller. And we know that this one diverges because this is p equals 1/2, which is less than 1. And so this means that this is even bigger than something infinite, so it also diverges. And next. So can we use the comparison test here? Let's see. So this is x over e to the 4x. So I know that you might not know that, yeah, so I can use the comparison test here, but it uses facts that we haven't been over, such as the fact that an exponential function grows more quickly than any polynomial. If you know that fact, then this is very easy, because this means that this is less than 1 over x to the, let's say, 17 or something, because e to the 4x grows even faster than x to the 17, and this becomes 1 over x to the 16, and so you have this side converging by the p-test, and so this is smaller than something that converges, so it must also converge. But since we haven't been over these relative growth rate stuff, you probably just want to use integration by parts to do this integral. So do u equals x and dv equals e to the minus 4x, and then you get dx should go right here. Du is equal to dx. V is equal to minus 1/4 times e to the minus 4x. And then the hard integral that you get after doing u times v is minus the bottom row. You have to do minus minus becomes plus 1/4 e to the minus 4x dx. And so that again becomes, right, just another factor of negative 1/4. So the whole thing is equal to u times v, which is x times minus 4x from 7 to infinity. This limit that, oh, I don't know why I wrote that infinity sideways. This limit you have to do using L'Hopital's rule. So if you use L'Hopital's rule, you'll see that the limit as x goes to infinity of x times e to the minus 4x is equal to 0. So that part disappears, and you have this integral, which amounts to minus 1/16 e to the minus 4x, and now you're, again, this is going from 7 to infinity, so you're looking at what happens as x goes to, I don't know why I wrote it sideways again, that's crazy. So you're looking at what happens here as x goes to infinity. This is negative exponent, so it's 0. So the whole thing converges, and they probably just do all that stuff here too. So converges. And that obviously diverges. Use the comparison test. Okay, so what is the, notice that these are all 1 to infinity type problems, and it's probably just the p-test over and over again. So let's do some of these. So x over the square root of x to the 6th plus 4. First we should come up with a hypothesis. And so in the downstairs here, you basically have the square root of x to the 6th, which was x to the x cubed. Then you knock off 1 for this one on top, and you get 1 over x squared. So this is basically like 1 over x squared. But now let's formally justify all that stuff. So this is less than x over square root of x to the 6th, which is equal to 1 over x squared. This one converges by the p-test. This is p equals 2. And so this one's even smaller, so it converges too. Converges. Now for the next one. You've got cosine squared x over x squared plus 4. So this is less than, notice that cosine is at most 1, so this is less than 1 over x squared plus 4. So at this point you could do the integral using inverse tangent, or you could observe that this is even less than 1 over x squared. This one converges because it's p equals 2, and so this one is convergent because it's even smaller. All right, and now you've got number 3 is an even easier version of number 2. So number 4, you've got 1 over e to the x times x squared. This is even less than 1 over x squared. This one converges because you have p equals 2, so this one also converges. And finally, for the last one, we have something that diverges, because it's basically like 1 over the square root of x, and so that would be p equals 1/2, which would be divergent. So let's prove it. So you've got 1 over 6 plus sine x, square root of x minus 0.5. So now my hypothesis is that this diverges, so I'm going to try to go up. So this stuff is greater than, so the smallest the denominator could ever be is 5. But let's go even further and just write a 1, because that's simpler. Then I'm also allowed to make the denominator smaller, right? Because that will make the whole thing bigger. So it's bigger than this. But this diverges because p is equal to 1/2. And you diverge whenever p is less than 1/2. And that's all. Oh, and then there's all those comparison things. I hope we're getting close to the end. Getting close to the end. So this one goes to minus infinity. This is arctangent. It does converge. It's a little bit more than, somewhere between pi over 2 and pi. So just do that integral using arctan. This one obviously diverges. So this one is sort of like x to the 1/3 power. Oh, but okay, so here the thing is you're integrating near, notice this integral is not improper because it's going to infinity. It's improper because the expression has a 0 at 5. And so this is going to be basically like the p-test, but this is sort of the, this is the 0-1 p-test, where the rules are reversed. We talked about this before. So this is p equals 1/3, and so we would guess that it converges because that's the rule. So now let's try to argue that. So square root of x minus 5. So we want to argue convergence. So we want to try to get less than something that that converges. So this is less than 1 over the cube root. Oh, sorry, it's not. Yeah, so this is a bit of a pain because the comparison test doesn't work. So I think what you have to do is just do the integral. It's not a very hard integral. You just do u equals x minus 5, and then, yeah. And you'll basically get an integral that's something like 0 to blah, I'm not sure what, of x to the minus 1/3 dx, and then you'll see that this converges, so converges. Now This one is the horizontal brontosaurus tail. Use the comparison test. P is equal to 3/2, which is bigger than 1, so it converges. This is basically P equals 2, so it converges. This is basically P equals 2, so it converges. Let's go ahead and formally do this one, because this one would be a difficult integral to actually evaluate. So we have x times square root x squared minus 1. So I believe my hypothesis is that this thing converges, so I want to try showing that it's less than something that converges. So what can I do here? I guess I could try to make this thing under the radical a square. What could I do there? So what about x squared, crap. Oh, you could transform it into... I'm gonna think, pause the video. Okay, I think I see a path to victory here. So notice that the square root of x squared minus 1 is the square root of x minus 1 times x plus 1. So this thing will get smaller if I change this to the square root of x minus 1 squared. Or sorry, I think the arrow goes the other way. So this is true, right? So this one is just x minus 1. And so when you put it in the denominator, the arrow goes the other way. So this is less than 1 over x times x minus 1. And what you get is 1 over x squared minus x. But this thing will get smaller if you pump this x up to an x squared. So this is even bigger than, let's say, x squared minus 1/2 x squared. And this is 2 over x squared. So this one converges. And now we've got a bigger one that converges. So we can use the comparison test to conclude that this one converges also. Was that legitimate what I did right here? I made the denominator bigger. That was a lie. I lied to you. So what can you actually do? You can only make the denominator smaller. Oh, but that did make the denominator smaller. I'm sorry. Yeah, I was right. Yeah, when you try to do it both ways, you're always right. It should just always say that the answer is yes and no to every question. So I replaced this with 1 over x squared minus 1/2 x squared. So this is indeed a smaller denominator eventually, because x squared is bigger than x, but it's negative. So this is fine. And so this is 2 over x squared, which converges, and that argument was right. Problem 45, there can't be too many problems left. There are, what values make, let's look at B here. What makes it improper? Either 2 or 5, because that makes the expression undefined at the endpoints. For this one, what values of P make the integral improper? And the answer is none. And for this one, the answer again is none. So check here. Oh, there says there is a singularity at x equals 0. Oh, that makes sense. Oh, right. So they're, sorry, no, they're just saying that there is no such p. So the answer is none, p equals 2 or 5, and none. (46). So why is this one improper? So it's because cosine of pi, so secant x is equal to 1 over cosine x. And cosine of 0 is 1, that's fine, but cosine of pi is equal to -1, okay, which is also fine, but you're integrating over a discontinuity at pi over 2. Let's clear all this up. So let's look at what we're talking about here. So here's 1 over cosine x, and so that's secant, and we're looking at it on this domain from 0 to pi, and at pi over 2, cosine is 0, so you have something that looks like this, zoop, and comes back down from infinity here. You're integrating over a discontinuity at pi over 2, so you have to break it up and do these two parts separately. So for instance, the answer is just going to be, what is 2 times the integral from 0 to pi over 2 of secant x dx, and so this is actually technically equal to 2 times the limit as t goes to pi over 2 from the negative side, the integral from 0 to t of secant x dx. So we take the antiderivative and we get 2 times the limit as t goes to pi over 2 from the negative side of natural log of secant x plus tan x with the limits from 0 to t plugged in. Alright, and so now let's actually plug in those limits. Notice when you plug in 0, you get 1, and natural log of 1 is 0, so the 0 limit doesn't matter. So we just plug in t, and this is 2 times the limit as t goes to pi over 2 from the negative side, natural log of the absolute value of secant t plus tan t. So let's put those things over a common denominator. That's 1 plus sine t over cosine t. All right. So now as t approaches pi over 2, the numerator is going to approach 2, which is a perfectly normal number, but the denominator is going to approach 0. So that means that this whole thing is going to be infinity, which means diverges. Zoop. So let's check our answer. And correct. Next problem. Good God, how many of these questions are there? Alright, so let's do this one and then I'm going to call it a day. How long is this video anyway? I'm spending my whole day doing this. Alright, so the formula for arclength is 1 plus f prime of x squared integrated on the interval of interest. So the f of x in this problem is, oh, it's the semicubical paraboloid. And so f prime of x is equal to 4 times 3 times x to the 1/2. And if I square that, Then I get 144 times x. So the integral that I have to do is from 2 to 4, the square root of 1 plus 144x dx. And this is an easy integral with u equals 1 plus 144x. Right, and then I said I was going to stop, but what comes next? I am going to stop because I'm really tired and I've done a ton of these.